Hey everybody, it's Mr. Roy. Let's talk some centripetal force problems. I'm going to be going through examples 4 through 8 from our uniform circular motion material, and these are all looking at centripetal force. So the center-seeking force, that's going to cause movement to keep things moving in a circle, and that force is pointing towards the center. Okay, let's jump in. Let's have a look at our first one. This one says a 1,200 kilogram car enters a level curve at 25 meters per second. If the curve has a radius of 100 meters, what's the minimum coefficient of static friction that will keep the car from slipping? Okay, first let's take a little look at what we're talking about. This is a curve where the car is going to be moving in circular motion. Now the whole thing isn't a circle, but this section, this particular section that we're looking at here, where it's going around this curve, that particular part of the motion is in a circle. So we can apply our any of our formulas for circular motion, and they're going to work just fine there. Now, important to note here that we are talking about a level curve. The questions you'll see from me will say level curve, and the textbook says a flat curve, and those just mean the same thing. So it's not a banked curve. There are a lot of um, curves. In reality, we bank curves because they help. The normal force going around that curve helps to propel your car, helps to give it a force towards the center. So the normal force actually helps keep you in a circle um, rather than going straight and sliding off, right? If we were to keep going straight, we just slide right off the road. So a flat curve is not actually how real roads are built. And hopefully after this, you'll start paying attention to how curves are actually banked in the real world. And in racing, we see them really banked in order to allow the cars to go a lot faster. So that's what we're talking about here. Okay, so with this car on a flat curve, we note that we're going to have, of course, have our force of gravity pointing down, and we're going to have our normal force pointing up. And we know in this case, those are going to be equal and opposite one another. So if we actually draw, this is what we're talking about from a side view, right? And if we actually draw our free body diagram, it's going to look like this one here. So we've got force of gravity down, equal and opposite, normal force up, and then we have our force of friction, which is what's keeping us in the circle. So this force of friction points that way. Now you may say that's weird for a force of friction to be pointing sideways, but as this car is going around the curve, the wheels are going to push on the pavement in order to try and keep this car in the circle, and the pavement is going to push back on the wheels. So that's Newton's third law, says we have action-reaction forces. So it's actually this force of friction between the wheels and the pavement, this sideways force that's going to keep us in the circle. If the road is too slippery and we don't have a nice, we can't have that frictional force, we're just going to slide straight off the road and off we go into the ditch. So we do need frictional forces when we've got a flat curve to keep us in the circle, otherwise we can't get around there. Okay, let's do the math involved for this. I'm just going to scroll down and give us a little more room here. And we'll get a thinner pen and we'll get to work. That's pretty good there. Okay, we'll write down our knows and need to knows first. We'll say our mass is 1,200 kilos. We got that out of the question. And we'll say our speed is 25 meters per second. And we'll say our radius for this question is 100 meters. You'll notice the picture above said 85 meters. I just grabbed that out of the textbook so you could see a picture of it, but that of course doesn't match our question here. So we notice that our force of gravity and normal force cancel out, so we've only got one force that's contributing to our centripetal acceleration, and it's the frictional force. So let's write our equation for that. So we're going to say, okay, net force we know is equal to the sum of the forces. That's how we always write Newton's second law. And we say net force is mass times acceleration, but in this case it's centripetal acceleration. And the sum of the forces, there's just one of them. Your book calls it Fs for static friction. I like to call it force of static friction, so like that. You could also just write it as Ff, force of friction, and that would be fine. I would know what you meant there. Okay, now we say, well, what is our force of friction? Well, we have a formula for that, right? We say our force of static friction is going to be coefficient of static friction times the normal force. And we know what the normal force is, right? The normal force is equal to gravity, so that's just going to be mg. So okay, let's put that in there. We're going to say force of friction is the coefficient of static friction times mg. We say, okay, how about our centripetal acceleration? We do have three different kinds of formulas for that. In this case, we're dealing with speed. So we're going to put in our speed formula, speed squared over radius. I notice I have an m on either side, so I can get rid of those. And that's going to clean things up a little bit for me here. And then on this side, I'm going to have speed squared over radius equals the coefficient of static friction times g. Ready to sub in and find some stuff out here. We'll say our speed is 25 squared, our radius is 100 meters, our coefficient of static friction times 9.8. Now I'm just going to kind of skip a little bit of the math here. We're going to take 25 and square it. Then we're going to divide that by 100. And then we're going to divide both sides by 9.8 to get rid of that 9.8 on the right. And we'll be left with our coefficient of static friction, which is going to be 0.64. We'll put a box around it. That's rounded off to 2 sig figs. So it's good to go. We know there's no units on coefficients of friction. Okay, so this is the minimum coefficient of friction we need for this motion. If we're going faster, we're going to slip. If we had a higher coefficient of friction, we could go faster. But for the speed that we're going at, this is how much friction we need in between our wheels and the pavement in order to not slip. Okay, let's have a look at another one here. Let's jump ahead. This one is looking at circular motion in with like something that's moving through the air. So in this case, we're talking about a vertical circle, right? So when we're talking about a vertical circle, let's throw a circle on here, like that, right? There's our circle. Now in this case, a plane is not actually going to, I mean, you can't do loop, it is possible to do loop-de-loops in a plane, right? But that's not usually what's going to be going on here. Usually what we'll be talking about is just the bottom part of the circle where the plane is flying through that circular arc. So as long as it's in that circular shape, we can use our formulas that allow us to look at circles. So I'm actually just going to draw the bottom of the circle here. And that's the part we're going to use. So it's going to look like this. Here we go. That's our circular shape. It's not perfect, but it is okay. Good enough for our purposes. And we say, okay, here's our plane right here. We'll just put it right there at the bottom of the circle. And now we know we have a couple of forces involved. So we say this is a circular dive. So we know that there are going to be two forces involved, right? We're going to have force of gravity that always points down. And then we're going to have we want to know what's going on with the pilot, right? So we're going to have the normal force of the pilot's seat pushing on their butt. If this was just the plane, instead of the normal force, we'd be looking at the force of lift, which is the wind as it flows over the wings, creating that force. But in this case, we're talking about the pilot. So it's the normal force of the seat pushing on their butt. So when they're going through this kind of dive at the bottom of the circle, they're going to really feel a lot of force, right? Kind of like that G-force video that we watched the other day. Okay, let's draw the forces that are going on. Now, I should also say, though, in order to stay in the circle, we need to always have a net centripetal force that's pointed towards the center, okay? So however these forces add up, they need to add up with a centripetal force towards the center, and that centripetal force is going to be the same anywhere in this circle. So if we're thinking about the circles, right, we could say, okay, here's our circle. At the bottom, we're going to have our force of gravity, and we're going to have our normal force pushing up. That's actually going to need to be a bigger normal force because it's going to need to overcome gravity and keep us in the circular shape. Whereas at the top of the arc, we've still got this same force of gravity, and now the normal force is actually pushing in the same direction. We're going to add those two forces together to create this centripetal force. And we're going to end up with the same centripetal force here as the centripetal force here. Those two are going to work out to be equal to one another, and that's why we stay in the circle. Okay, so let's draw our forces on this this one right here. First of all, we got our force of gravity that's pointing down. It's going to look kind of like that. There's our force of gravity, and we know force of gravity is mass times g. We say, okay, we're not descending though, we're accelerating towards the center. So we have to have a force that's going to beat that. That's going to be our normal force. And when we add those two together, we're going to have a centripetal force that's going to look kind of like that. That's our actual centripetal force. That's our, which is equal to our net force, right? When we add all of our forces together, that's the one we get. Okay, so let's actually turn this into some math, shall we? We'll say, okay, um, first of all, nose and need to knows, mass is 90 kilos. Radius is going to be 1.4 kilometers, and we're going to turn that into, turn that into meters. So we'll say, okay, that's going to equal 1,400 meters. Our speed is 720 kilometers per hour. Notice I didn't say velocity because the direction is always changing, so the velocity is always changing. The speed is what's constant. In order to turn that into meters per second, we need to divide by 3.6. And so that's going to end up giving us exactly 200 meters per second. So that's the stuff we know when we've converted all our units, and now they're going to cooperate with one another really well. Okay, let's actually look at the math involved here. We're going to say net force is equal to the sum of the forces. That's how we always start a question like this. We say, okay, the net force is equal to mass times centripetal acceleration. And the two forces involved are a couple of them. We got our force of gravity, and we have our normal force. And in these circular problems, we always have those two forces. But the direction they point is going to depend, right? So let's choose our directions now. We're going to choose down is negative and up is positive. And that's going to help us figure out which way to go. So we know our net force, which is our centripetal force, has to be pointing up. So we're going to leave this as positive, okay? This is going to be a positive number because we know it has to be pointing up. If we were at the top of the circle, we would know our centripetal force would have to be pointing down, and we would have to put a negative in front of this in order to do that calculation. Okay, let's sub in. We're dealing with speed, so our centripetal acceleration we'll use our speed version of the centripetal acceleration formula and plug that in. Force of gravity is mass times g, and our normal force. Okay, let's sub some values in here. Now you may be one, first of all, saying, oh, haha, look at that. We got mass there and we got mass there. Let's cancel them out. Careful. You can't do that. We don't have mass in both terms on the right side, and we'd have to divide mass out of both terms. So we're not allowed to do that. If you are tempted, you must resist the temptation. Okay, let's plug our values in. We got 90 kilos for the mass. For the speed, we got 200 meters per second, so we'll put 200 squared. For our radius, we'll go 1,400 meters. On the other side, we've got 90 kilos again. And for g, we've got, it's down, right? So negative 9.8. Our acceleration due to gravity, and we got our normal force. Let's get ourselves a little more room here. Okay, let's clean this up a little bit. If we take 200 and square it, and then we divide by 1,400, and then we multiply that by 90, we're going to end up with 2,571.428557. I'll keep a bunch of decimal places for now, just to make sure I'm being precise. On the other side, 90 times negative 9.8 gives us negative 882 plus our normal force. Let's add 882 to both sides to move it over to the other side. And we're going to end up with a normal force of 3,453.42857. Let's round this off. We know we're going to go to two significant digits because we look at our input data and that's what we got. That's as precise as we can be. So we'll say the normal force, it's got to be 3,500 newtons, and we know we can give it a direction. In this case, it's pointing up It's got to push up on the pilot to counteract gravity and keep the pilot in that circle. So that's the force that we're going to experience. If we fly in a circular shape, that's the normal force that the pilot will feel the seat pushing on their butt to keep them overcome gravity and keep them in that shape. Now, if we were at the top of the circle, we would instead have put a minus right here. And that would give us a pretty different answer because both our centripetal force would be pointing down and our force of gravity would be pointing down. But in this case, we have one pointing down and one pointing up. Okay, let's move on to our next one. This is number 6. A 1.5 kilogram ball is attached to a 3-meter long rope and whirled on a horizontal circular path on a frictionless surface. This is a very idealized problem, not super realistic to real life, but it's going to help us learn the concepts that we can apply to similar situations. Of course, if something was orbiting in outer space, there wouldn't be any friction, so this would be an example of that, of the same type of mathematics that you'd be using in that situation. I like to think about this as taking a curling stone and tying a rope to it and then spinning in a circle, because the friction between ice and a curling stone is so small, it's very close to being frictionless. Okay, so let's figure out how this is going to go. We only have, let me put a circle in here first so we can kind of draw our situation. Here's our circle. All right, so we'll move that over. Sure, let's go red. We're going to say, okay, it's a 3-meter long rope, so our radius, we could draw it in any direction. That's going to be 3 meters. And it's a mass of 1.5 kilograms. And we're also given some information about 16 revolutions in 10 seconds. That's going to be helpful for us because we are going to figure out the force of friction, or we're going to figure out the frequency here. I knew it was an F. Okay, so first we'll say let's find our frequency. That's going to be our first step. We'll have to think back to grade 11 physics, right? So we'll say frequency is number of cycles over the amount of time that it takes. So number of cycles is 16 revolutions in 10 seconds. So we end up with a frequency of 1.6 hertz. That's our unit for frequency. Okay, now we want to find the tension in the rope. That tension in the rope is going to be equal to our centripetal force, because in the end, that's the only force. If we actually take a side view of this, right? Let me draw my curling stone here. There's my nice little curling stone. It's going around the ice. And I want to draw a free body diagram, right? I normally shouldn't draw the stone if I'm drawing a free body diagram, but whatever, good enough for now. Force of gravity, normal force, they're equal and opposite, right? So they're going to cancel each other out. So the only force we've got going on here is this force of tension towards the center. So that means that's got to be our centripetal force, because that's it. There's only the one force. We don't have to add a few forces together to be our centripetal force. So let's use Newton's second law like we always do. Net force is the sum of the forces. Net force is mass times centripetal acceleration. What's the sum of the forces? Well, gravity and normal force cancel out. We're just left with this tension force. Okay, now for centripetal acceleration, we're going to choose the version of the formula that has frequency in it. Really easy to make a mistake and forget to square one of the pieces, so be cautious when you do this. 4 pi squared times the radius times the frequency squared. That's going to equal our force of tension. Okay, let's plug some stuff in and see where we go from here. Mass, we got 1.5 kilos, so we got our 1.5. The 4 and the pi squared, I'm going to keep together because those are just all regular numbers. I would recommend using the pi button on your calculator. It will have one, and it'll keep it more precise than punching in 3.14. Radius is 3 meters. Frequency is 1.6 hertz, and that's squared And all that is going to equal our force of tension. So this is some calculator work, right? 1.5 times 4 times pi squared times 3 times 1.6 squared. That's going to give us our force of tension when we work all that out. And that's going to be 454.79137. Okay, let's add some units and directions and all that good stuff to finish off this problem. So force of tension, let's round it off to 2 significant digits. It's going to be 450 newtons. Now this is a tension force. The question doesn't say give me the magnitude of the tension force. It says give me the tension force, which means it does need a direction. But the direction is constantly changing. So here's what we can put in for our direction. We'll say it's towards the center. There we go. I'll put a box around it. So that's our final answer. Okay. So that's another horizontal circle. Those ones tend to be a lot easier. We usually only have the one force that's involved with them. Let's have a look now at a vertical arc. Again, we got a ball and we're spinning it and we're dealing with frequency here. So a 250 gram ball is attached to a 1.4 meter long rope and whirled in a vertical circular arc. If the frequency of revolution is 2 hertz, determine the maximum and minimum tensions in the rope. Okay, first of all, let's just try and come up with the stuff we know and need to know. Mass, we're going to say it's a quarter kilogram. Our radius is going to be 1.4 meters. Our frequency is going to be 2 hertz. Okay, and we say this is a vertical circle. So that means we're going to have 2 forces that we're dealing with here. Those 2 forces, what are they? We got a force of gravity, always, and we have our force of tension. So we're going to have to draw those. Now our force of gravity is always pointing down. Our force of tension is going to point towards the center of the circle. So at the bottom, it's going to point up. And at the top, it's going to point down. Let's just draw a quick little sketch of those, right? Here's our thing at the bottom. Gravity's pointing down. Tension's pointing up. Next one, at the top, gravity's pointing down. Tension's also pointing down. So we need our net force, our centripetal force, to be equal in both cases. That means at the bottom, our force of tension is really big. It's got to overcome gravity and give us enough force to keep us in the circle. At the top, it's working with gravity, so it's actually going to be very small. It needs to combine with gravity to equal our tension force. Okay, so we know our max tension is going to be at the bottom, where the force of tension has to overcome force of gravity. Let's write that in here. We'll say max tension is at the bottom, where the force of tension must overcome the force of gravity. Our minimum tension is at the top, and we'll say where force of gravity helps to keep it in a circle. Ooh. And now it's yellow. Helps to keep it in a circle. Please forgive my tablet writing here. It's a little tricky to write on this tablet. Okay, so it's going to be important for us to recognize that our centripetal force is always going to be the same at the top or the bottom. But how we get that centripetal force by combining gravity and tension is going to be different, right? When it's at the bottom, big tension force overcomes gravity and gives us the extra we need to keep us in a circle. At the top, it combines with gravity, both pointing down, to combine to be the amount we need to stay in the circle. So when we actually write our math, it's going to look like this. We're going to say the net force is equal to the sum of the forces. We're used to that. But here's the little trick we're going to do. Because we're going to look at the top and the bottom, and this will save us a little bit of time, we're going to put a plus and a minus in here. And rather than having to do the whole calculation once with a positive and once with a negative, we're just going to do it once with a plus minus. And that'll save us a bit of work. You could, if you wanted, do it as two separate calculations. That'd be fine. But this is going to make things a little quicker and a little easier. Now, why we have our plus minus, let's remember, we're going to define our directions. We're going to call up positive and down negative. And we're saying that our net force, which is equal to our centripetal force, is pointing up at the bottom and down at the top. If I change to red here for a minute and draw my circles with just my centripetal force, I got my centripetal force here, and I got my centripetal force here. Those are going to be equal. But the forces that make them up are going to be different. Okay, let's keep going with our calculation here. We know our net force is mass times acceleration. It's centripetal acceleration in this case. The sum of our forces are the two forces. We got our force of gravity, and we have our force of tension. Okay, let's plug some stuff in here. We know for centripetal acceleration, we're dealing with frequency. So we're going to put in our frequency formula. So I'll say mass times 4 pi squared r f squared. Force of gravity is going to be mg, where g is going to end up being a negative number. And my force of tension, which I want to find. Let's keep rolling here. Let's plug in some numbers. Mass is 0.25. We've got 4 pi squared. We've got radius of 1.4. We've got a frequency of 2 squared. And on the other side, we got a mass of 0.25. We've got acceleration due to gravity. It's downwards always. So even for the two cases, we can put that one in because it's always the same. And we got our force of tension. That's the one we're going to find out. Okay, let's clean this up a little bit. I go 0.25 times 4 times pi squared times 1.4 times 2 squared, which is 4. Here's what we end up with. 55.26978. That's plus or minus, depending on which direction, if it's at the bottom or the top of the circle. Negative a quarter times 9.8, that gives us negative 2.45 plus our force of tension. Okay, I want that force of tension, so I gotta add negative 2.45 to both sides. So this is what we're going to end up with. We're going to end up with our force of tension is equal to 2.45 plus or minus 55.26978. And if I go back up to my red circles here, I see in one instance I have it pointing up, and in one instance I have it pointing down. That's my centripetal force, which is my net force, which is what I calculated on the left. So that makes sense that it would be plus or minus. So we could, again, do one calculation and then another calculation. This is going to save us some time by doing the plus or minus. So that means we're going to have two values for our force of tension. So our max, our force of tension is going to be 58 newtons when we add those two together, and it's pointing up. Our minimum tension is going to be 53 newtons. That would be negative, right? 2.45 minus 55 and stuff. So we're going to end up with a negative value, which would mean down. So there we go. There's our two different forces. At the bottom, it's 58 newtons pointing up. At the top, it's 53 newtons pointing down. That's our tension in the rope. That when you add gravity in there, it gives us the same centripetal force at the top and the bottom, keeping us in that circle. And the tension in the rope will just change automatically, right? The tension in the rope will change automatically in order to make sure our centripetal force is the same, unless the rope breaks. If there's too much tension, the rope would break and the thing wouldn't move in a circle anymore. Okay, that's number 7. Let's move on to our last one here, number 8. Here we go. This one says a 1,500 kilogram truck travels around a frictionless curve having a radius of 100 meters. If the curve is banked at 20 degrees to the horizontal, at what speed must the car travel to maintain a constant radius? So a frictionless curve, what we're talking about here is a super duper icy road. No friction, you're just sliding. But if the road is banked enough, you'll still get around the curve as long as you're not going too fast, right? We'll still get around the curve even if there's no friction. We don't have that static friction to allow us to go in the turn. As long as it's banked enough, we'll be okay. So we need to figure out what speed can we go without sliding off. So again, now we're talking about our banked curve this time. Same situation, we're going in circular motion around the corner, but we've got a banked curve that's going to help us, and we have no friction between our tires and the road. Let's have a look at what we're talking about here. Now this is 85 meters, that's not correct, but that's just I wanted to show you an example from the book. We've got 100 meters for this particular one. Okay, so let's actually draw a diagram of what this looks like, right? We're going to have some forces involved here. We're obviously going to have our force of gravity. We know about that. We're going to have our normal force. Now, you might be expecting, hey, I remember doing ramps. I remember we've got this component of our force of gravity, and the normal force is equal and opposite that. Well, that's not actually the case here. That's only when something is sitting on a slope, right? Like a skier, for example, or a block sitting on a ramp. In this case, though, we're actually going forward around the curve. And you can imagine if you've ever been on like a roller coaster that goes around a curve or a car that goes around a bank curve really quickly, you feel like you're getting pushed down into the seat. That's actually the normal force pushing up on you. So the faster we go around that curve, the more it's going to push up against us. Okay, so that normal force, we have to be careful. We actually cannot assume that this normal force is going to be equal to the perpendicular component like we're used to seeing. It's not. It's actually going to be a bigger normal force in this case as we're going around the banked curve, and that normal force will depend on how fast we're going. Okay, so let's actually look at a free body diagram here. Here's our free body diagram. We got our incline, we got our force of gravity, which is mg. We're used to that, no problem. And then we've got our normal force. We don't actually know what our normal force is, right? It's going to depend on our speed. So we're going to need to work this out. Now our normal force, we can actually take the components of the normal force. It's got two components. It's got, let me get out my highlighter here. It's got a vertical component, right? And we would say that's going to be Fn, normal force, times cos theta, because we know that this angle in here is going to equal this angle over here. So we say, okay, Um, Let me get rid of that yellow there. Back to my pen. So we'll say, okay, we got this component here, and then we also have this component of it right here. This component here is going to be the component of the normal force that keeps us in the circle. It's pointing towards the center. That is our centripetal force. So that component pointing towards the center, that's what's going to keep us in the circle. This is the one we really care about right here. Okay, and that's going to be the normal force times sine theta, because it's opposite that angle theta. So normal force times sine theta, that's really important. That is the component of the normal force that keeps us in the circle. The upwards component of the normal force is going to equal gravity. This one right here is going to equal gravity because we notice we're not sinking into the roadbed or flying away. Okay, tricky stuff, right? Let's have a look at our solution for this. First thing we're going to say is we're going to have a look at vertical forces. Forces in the y direction. We notice that we have a constant radius, right? If we go back up here, we say, what is the speed the car must travel at to maintain a constant radius? That means we're not slipping down our curve because we're going too slow. We're not sliding off the right side of our curve because we're going too fast. We're maintaining this constant radius. This radius right here, that's going to be constant. Okay, so that means our upwards and our downwards forces need to be balanced. If they're not balanced, if the downwards force is too strong of gravity, we're going to slide down the ramp. If the upwards force is too strong, we're going to slide up and off the ramp. We don't want either of those. We want a constant radius. So we say, okay, with vertical forces, if we see this word constant radius, that's going to tell us that the vertical forces are balanced. And we can actually write that mathematically, right? If the vertical forces are balanced, we'll say the net force in the y direction is going to be equal to the sum of forces in the y direction. And if the net force, if the forces are balanced, our net force is zero. So our net force in the y direction is zero. The forces are balanced. Let's write down our sum of our forces here in the y direction. We say, okay, in the y direction, we got our this upwards force, Fn cos theta. Okay, that's one of them. And then we have our force of gravity, which is just going to be mg, right? So let's rewrite that. We'll say normal force, Fn cos theta, plus m times g. Okay, let's keep working here. I know g is going to end up being a negative value, so I'm actually, get back here, I'm actually going to write this in order to make my math turn out nicely, because I know that's going to be a negative value. I'm going to write this as negative mg, and I won't have to worry about plugging in a negative value for g. I can just plug in 9.8. Okay, so let's move the mg over to the other side. We end up with mg equals normal force times cos theta. And let's solve for normal force. So we'll say normal force is equal to mg over cos theta. So that's a relationship for a normal force. Now this is complicated. Stick with me here. We're going to get to one that we can use for all banked questions. Okay, we won't have to do this every time. This is kind of like getting us to an easier place that we can reuse over and over again. Let's talk about our horizontal forces. Our horizontal forces we're going to say net force in the x direction equals the sum of forces in the x direction. So I say, okay, what are the forces in the x direction? Well, that's the force causing us to stay in a circle, right? To be in a circular motion as we go around this curve. So we say, well, what's our net force? It's MAC. It's mass times acceleration, centripetal acceleration. What's the sum of forces in the x direction? Let's look at our diagram. It's right here. It's the normal force times sine theta. Okay, so normal force times sine theta. That's the only force in the x direction. Okay, we did work out an equation for the normal force over here, right? Right here, we got this equation for the normal force. Why don't we like plug that in over here? Let's go for it. So we'll say mass times centripetal acceleration is the normal force, which you know is mg over cos theta times sine theta. So I just subbed mg over cos theta in. That's nice. I can get rid of my m's. I got an m in each term on each side, so I can divide them out. So I'll say, okay, cool. My centripetal acceleration is going to be equal to g times sine theta over cos theta. Sine theta over cos theta is tan theta, right? So I could say g times tan theta is my centripetal acceleration. This is an important one. So let's put a box around that even though it's not a final answer. This is one you probably want to put on your yellow sheet. And let's write ourselves a little note. I think I'm going to type this just so I can save myself a little bit of time here. Let's shrink our typing down to that size there. And we're going to say works for all road banking. And you often see these in physics, so I'll mention it here. Conical pendulum questions. That's when you have like a cone-shaped, a pendulum that's moving in a cone shape, which pendulums do, is it comes up more often than you think. So I'm just going to park that here. And let's go back to my pen and I'll draw a little arrow over to remind us of this. So that's going to be good for all road banking questions, right? Anytime we got a road banking question, we can pull this formula out, and that's going to be useful for us. So that's going to save us a lot of time, right? We don't have to rederive that every time. Okay, so let's go back to our question and see where we're at now that we have this new formula for centripetal acceleration in a road banking question, right? We'll say, okay, centripetal acceleration. What is centripetal acceleration again? We can write it as the speed squared over r. So I'm just continuing from where I left off, but I just stopped there for a second to remind myself of that important formula. Times g tan theta. Let's take our r and multiply that up over. So we'll say v squared equals r g tan theta. And then let's take the square root of both sides. So we end up with v equals the square root of r g tan theta. Okay, let's plug in some values here. Radius is 100. P is 9.8. Tan theta is tan of 20 degrees. Let's multiply all those together. Take the square root. We end up with 18.88626. Let's round that off to two significant digits. That's going to be 19 meters per second. Now we got to go up and check. Did this question say speed? At what speed must the car travel? Speed is a scalar. So we don't have to put a direction on here. We just leave it as a scalar like that. And we're done. Whew. Okay. It's a big, ugly problem. Pretty difficult one to do. The key thing I want you to take away from this is our centripetal acceleration in road banking questions is equal to g tan theta. It's a nice little shortcut we can use that we got to, and we can work from there whenever we're doing road banking questions. Tricky one, but I hope this has helped. Okay, thanks everybody. I'm going to stop there. I'll see you soon. Bye for now.